So today's speaker is Dr. Jacob Barandes. Jacob received his PhD in 2011 at Harvard University's physics department, where he now is a lecturer. At Harvard, he's also the director of the Graduate Studies of Physics. Jacob's research combines the two areas of physics philosophy and philosophical physics. His expertise lies in foundations of quantum mechanics, the metaphysics of causation, the philosophy of probability theory, field theory, and general relativity. Recently, Jacob published a big paper on a new take on quantum theory, and today we're very much looking forward to hearing more about this. So with that, Jacob, thank you very much for joining us, and the virtual floor is yours.
Thanks so much, and I want to thank David and Hugo for the wonderful invitation. I'm really happy to be here, and it's nice to be talking to everybody here today. If I can go ahead and share my slides, is that okay? Excellent, thank you. All right, we have an ambitious agenda, so I'm going to get started. The title of my talk is the Stochastic-Quantum Theorem and Quantum Simulations of Stochastic Processes. This theorem is laid out and proved in the first of these two archive papers, and then its further implications are worked out in the second paper. Again, we have a lot I'm going to talk about, so I'm going to get started. All right, let me say a few things about quantum simulations of stochastic processes. So what could quantum computers be useful for? Well, solving hard deterministic math problems, for example, factoring numbers, search problems, solving hard optimization problems, sampling from static probability distributions. These are some of the most well-known and hoped-for applications for quantum computers. Perhaps the most obvious is simulating genuinely quantum systems. There's also been some recent work on developing algorithms for quantum simulations of dynamical probabilistic processes, by which I mean stochastic processes. Stochastic processes are processes that unfold according to laws that can at least be approximated as probabilistic. And stochastic processes give good phenomenological models for many real-world systems. Now, major question is whether there exist algorithms that can provide a quantum advantage for these stochastic simulations in much the same way that we think there's a quantum advantage for various deterministic math problems. What kind of quantum advantage could we have? Well, these quantum simulations might take asymptotically fewer steps. They might require less memory overhead. There was a paper in 2021 by Corseco and Listaglio that examined the question which stochastic processes can be embedded in a quantum channel, a GKLS quantum channel. An earlier paper by Binder, Thompson, and Gu studied actually in particular non-Markovian stochastic processes. And by this, they meant what we typically mean by non-Markovian, which is a process that may have a memory, where the laws are probabilistic, but where the probabilistic laws depend in a non-trivial way on the past. They were interested in non-Markovian stochastic processes that approach stationary probability distributions, denoted by pi, over long times. And then the question was, how does the entropy of that stationary probability distribution and the necessary memory size, how do they scale with various parameters of the problem? And can it be shown that if you simulate a stochastic process of this kind with a quantum simulator or a quantum computer, can you show that you can actually get gains in these metrics? So these efforts are not systematic. People are making guesses and trying things out, but there isn't anything like a systematic way to understand the scope of these kinds of problems, the degree to which quantum computers might provide an advantage. This is actually an extremely good opportunity to maybe step back and take a more foundational perspective. And that's what I'm going to be doing in this talk. So let's step back and take a really foundational perspective. Let's talk about how scientists themselves talk about what they do. So on the one hand, scientists, and by this I include scientists broadly speaking, from early universe cosmologists to ornithologists, they talk about numerous phenomena that physically happen. And maybe they happen deterministically, maybe they happen according to probabilistic laws. On the other hand, textbook quantum theory, and by this I mean the quantum theory in our textbooks based on the axioms handed to us by Dirac in his book in 1930 and von Neumann in his book in 1932. Textbook quantum theory based on these axioms is an instrumentalist and operationalist recipe. Instrumentalist in the sense that it's a set of mathematical tools for generating predictions of things that we'll see empirically, and operationalist in the sense that things are defined in terms of the operations that one does to realize them or observe them. It's a recipe that narrowly predicts only the following things: measurement outcomes, measurement outcome probabilities, and expectation values. And by expectation values here, one means statistical averages of measurement outcomes weighted by measurement outcome probabilities. And I'm really emphasizing that because there's a tendency by some to pretend that these expectation values are like the expectation values in statistical mechanics, which are really averages of phenomena taking place. The expectation values generated as predictions from textbook quantum theory are conceptually different. All of these outputs of the textbook theory are about measurement outcomes and their probabilities. So just from a basic conceptual standpoint, these two pictures, on the one hand, how scientists talk about phenomena occurring of all kinds, and on the other hand, the output of textbook quantum theory, are just phrased in manifestly and categorically incommensurable ways. They're just talking about different things. Even worse, activating the measurement outcome predictions of the textbook theory requires at some point deciding when you can say poof and magically invoking a measurement, which the textbook theory does not define. Now, this isn't such a big deal maybe in tabletop experiments where at the end of the day, we are just doing measurements on systems. But if you're working in quantum gravity, and my own background is in quantum gravity, or in cosmology, well, you can't stand outside the system and do a measurement on it. You're embedded inside it. And so you actually run into some pretty basic first-order questions about the applicability of the textbook theory. Now, one hypothetical way to get around this, and the way that one often hears from people, is that you can appeal to decoherence to try to define or axiomatize what counts as a measurement. Define in the sense that you take the axioms we already have from the textbook theory and somehow get measurements out of them as some kind of rigorous consequence. Or axiomatize in the sense that maybe we have to add a special measurement axiom that can be defined in terms of decoherence. So in principle, the defining and axiomizing approaches are not exactly the same. But there are a few fundamental reasons why no one has succeeded beyond hand waving. And there's a lot of hand waving. Often when I have conversations with people, they'll give me an explanation and their hands will literally wave. And I'll point it out to them. So one reason is that decoherence can only change which basis diagonalizes your density matrix. Density matrices are always diagonalizable in some basis, and all decoherence can do is change which basis that is. At no point do we get a poof that singles out one definite outcome. And moreover, decoherence is only ever approximate. So in order to get these arguments off the ground, you have to assume some sort of unphysical idealization, like waiting an infinite time or running infinitely many experiments, or assuming your system has infinitely many degrees of freedom. We're not sure that any of these things are true. We certainly can't do infinitely many experiments or wait infinitely long. And so one has to ask whether these are really relevant. People throw around ideas of limits here, but they're using them in a distinct way to try to get decoherence off the ground as a way to explain measurement. And it doesn't really work. And despite much effort, no one has come up with a crisp, satisfactory account.
So I have a question here, Jacob.
Yes, please. Please, yes. Questions are good.
Someone in the audience asked if you could comment on the approach of invoking a many worlds global wave function picture. It's such a fantastic question that I'm about to address it on the next slide. So that's an excellent question. Good timing then.
Yep, good timing. That's exactly where I was going. Thank you. So excellent question. And if I don't answer it satisfactorily, please come back and re-ask it. Okay, so an alternative, should we reify the ingredients in quantum theory? Can we resolve this incommensurability? On the one hand, the talk about phenomena, broadly speaking, happening. On the other hand, textbook quantum theory just generating measurement outcome predictions. Maybe what we could do is take the mathematical ingredients themselves and make them metaphysically real, make them phenomena, say that they're really, they're phenomena themselves, and those phenomena are happening. Well, what ingredients are even available? Well, we've got Hilbert spaces over the complex numbers. We've got state vectors and wave functions. We have density matrices and self-adjoint linear operators that represent our observables. We have time evolution operators and Hamiltonians. And this idea of trying to reify these ingredients, this is basically what one tries to do in an Everettian approach to quantum theory, like the many worlds interpretation. Take these ingredients to be the phenomena, and the things that happen to them are phenomena happening. Well, so one immediate problem, at least on its face, is that these ingredients don't live in 3D space or 4D spacetime or anything like it. But maybe, and this is what people who favor the Everettian approach will often argue, maybe we can get around that with some notion of emergence. Maybe our 3D spatial reality is in some sense emergent from some other reality, some vector twirling around in a high-dimensional Hilbert space over the complex numbers. Well, there's actually an immediate reason to be skeptical about whether this can work. And one way to see why this is a problem is to notice that quantum theory contains a relatively unrecognized form of gauge invariance. I know I've had many conversations with people who think about quantum foundations, and as far as I can tell, this is not widely appreciated. And it's actually a pretty severe problem for these sort of mathematical reification approaches like the Everettian approach that try to imbue the mathematical ingredients with a definite physical phenomenological meaning. If we let V of t be any time-dependent unitary operator, we can do the following gauge transformation, which leaves all the empirical predictions of the textbook theory invariant. You take your wave functions or state vectors and multiply them by this unitary. Now notice, this is a time-dependent unitary. This is not a constant unitary that would just correspond to a basis transformation. So we transform wave functions by multiplying them by this unitary. Density matrices transform by a similarity transformation, as do observables. Time evolution operators transform almost like a similarity transformation, but because they connect time 0 to time t, you'll notice that V dagger there on the right actually acts at time t equals 0. And because of that transformation law of the time evolution operators, you can show that Hamiltonians transform this way, which remarkably is exactly like a non-abelian gauge potential. This is identical to the transformation formula of the matrix valued gauge potentials that one finds in quantum chromodynamics or other non-abelian Yang-Mills gauge theories. And what it means is the Hamiltonian is strictly speaking not an observable at all. It's more like a gauge potential.
There is a question already here.
Yes.
So
please go ahead.
And maybe you were again about to comment on this, but someone asked, what is the question? What's the difference between the Hamiltonian and any other observable?
Very good question. Yeah. So it is true that if you pick a particular V of t, meaning you pick a particular unitary frame, then the Hamiltonian will be some self-adjoint operator. And you can, if you want, introduce an observable and say that observable agrees with the Hamiltonian in that frame. So for example, if you're studying a particle in 1D, your Hamiltonian will be something like p squared over 2m plus potential. And you can say, okay, that's the energy of my system if I want. That's kinetic plus potential energy. If I do this gauge transformation, the Hamiltonian will simply not agree with kinetic plus potential anymore. It'll become something totally different. You can still say that there is this observable kinetic plus potential, but the Hamiltonian simply won't agree with it. And this is not unique to quantum theory. This also happens, and I don't have time to talk about this in detail, but this happens in classical Hamiltonian mechanics as well. In classical Hamiltonian mechanics, we can do canonical transformations, which turn out to be extremely analogous to what I'm just doing here. And canonical transformations will change what the Hamiltonian looks like, even though they won't change any of the physical observables that you actually extract from the theory. So it's an excellent question. The Hamiltonian can coincide with observables, but the Hamiltonian will vary from a choice of V of t to another, one choice to another. But anyway, what this establishes, right, is that many of the mathematical ingredients we want to talk about in the textbook theory are more like gauge variables, like in electromagnetism. And we don't usually assign a direct physical meaning to the gauge potentials of electromagnetism precisely because they're just so radically non-unique. So all these Hilbert-space ingredients are gauge dependent. Again, that suggests their physical meaning is highly suspect. And actually, you can use the transformation of the wave function to map any state vector trajectory in the Hilbert space to any other state vector trajectory. So if you thought the trajectory of a state vector or a wave function in the Hilbert space contains some well-defined physical meaning, it just doesn't. State vector trajectories don't contain any gauge invariant physical content. Okay, well, if we're doing electromagnetism, we would say, all right, well, what are the gauge invariant quantities? So what are the gauge invariant quantities in textbook quantum theory? Well, they're just measurement outcomes, measurement outcome probabilities, and statistical averages of the former or of the latter, that is expectation values. But well, then we're right back to saying that the only ingredients we can rely on are the stuff that we were saying was just instrumentalism and operationalism. And we're back to appealing to magical poofs to make measurements happen. Now, I can't talk in this today about the other issues with Everettian quantum theory, although I'm happy to talk about them as well. But you can, if you put all this aside and try to build the Everettian approach, what I would strongly argue is that you end up stacking many speculative metaphysical hypotheses on top of each other. Again, I can talk more about that if people have questions, but it's one reason why, even beyond these arguments, I'm very skeptical of the Everett approach. Okay, so what ingredients can we find to provide a genuinely physical foundation of quantum theory where phenomena happen? That's a good motivating question. And if we're at it, why not? We should also address, like, why is quantum theory based on all these axioms anyway? Right? There's a huge list of axioms if you go and write them all out. We usually don't show all these axioms to newcomers. And we say we're not going to show them all the axioms because we think they're too hard. But I think we don't want to show them to students because if they saw just how many and how complicated there were, people would think there was something seriously wrong with quantum theory. And I think I would agree with them. These axioms involve a lot of very exotic things: complex numbers, Hilbert spaces, linear unitary time evolution, the Born rule, non-commutative algebras. Why? Why all these ingredients? Can we get rid of that magical poof we need to do for measurements? Why do the equations of quantum theory resemble those of classical statistical mechanics? For example, the Liouville equation in classical statistical mechanics bears a strong resemblance to the von Neumann equation in quantum theory. What connection, if any, is there between stochastic processes and quantum theory? After all, they both involve probabilities, vectors, and matrices. Is there some interesting connection here? And thinking more about stochastic processes, they often involve invoking the Markov approximation, which I'll talk about in a little more detail later. This idea that that the past is irrelevant, that stochastic processes can be treated as though they're memoryless, and all you need is present information to make future predictions. We often make this approximation to make things simple, but is there a way to justify, to get it off the ground from theoretical first principle reasoning? Well, addressing these questions, I'm going to argue, leads to a useful formalism.
Sorry, Jacob.
Yes, please.
And do tell me if you want me to kind of hold off.
Oh, it's okay. These are good. These are good questions. Go ahead.
But this might be a quick one as well. So if you go back to the last slide here. So someone asks if you can give an example of how the Markovian approximation is made in quantum theory.
Oh, I'm gonna come back to quantum theory in a moment. Right now, I'm talking about the use of the Markov approximation used for simulating classical stochastic processes. In fact, when you mention a stochastic process, when I mention it to my colleagues, they often assume I'm talking about a Markov process, like a Markov chain. And the question here is why we make that assumption beyond merely the fact that it's simpler to model systems that way. Now, the Markov approximation is also used in quantum theory. For example, the Lindblad equation, or the GKLS equation, the GKLS master equation, is an example of what's called a quantum Markovian process. And also, we make the quantum Markov assumption also to make things simple. And part of what I'm going to try to do is explain where some of those simplifications come from on first principles grounds, rather than just saying to make things easier. Good question. So addressing these questions will lead to a useful formalism for modeling a large class of stochastic processes, importantly beyond the Markov approximation. And in particular, if we can model stochastic processes in a very general way beyond the Markov approximation, then we have a platform for asking under what first principle circumstances do we expect to get the Markov approximation. Like, you can't justify the Markov approximation after you've already made it. The goal here is to start with a more general approach, and then from within that more general approach, explain where the Markov approximation comes from. And this formalism will turn out to be quantum theory itself. So in a sense, just like when you're doing classical mechanics, we have analytical mechanics, the Lagrangian formulation, the Hamiltonian formulation, and so forth, for studying and designing systems, right? For engineering, for defining choices of dynamics, we have the Lagrangian and Hamiltonian formulations. The claim is that there's going to be a class of systems, a class of stochastic systems. They're called generalized stochastic systems. This is defined in the first paper. And that they have their own analytical mechanics as well. And that analytical mechanics is just quantum theory. Quantum theory is the analytical mechanics of these generalized stochastic systems. So what Lagrangians and Hamiltonian formulations are to standard classical mechanics, quantum theory is to generalized stochastic systems. And this gives a new formalism. that goes alongside the path integral formulation, the Hilbert-space formulation, and so forth. And the hope is this formalism also potentially points to new algorithms for quantum simulations of stochastic processes. So said another way, consider the following grid. We've got classical physics and quantum physics. For classical physics, we have the most directly physical formulation, equations of motion, phenomena really happening, described by some mathematical layer of labels on things, and explicit equations that explain how those things change, how phenomena happen to them. And then we have the functional Lagrangian formulation and the first order Hamiltonian formulation. The first order Hamiltonian formulation is where you find enough new variables to express the equations of motion as first order and time differential equations. Well, in quantum physics, we have a functional approach, the path integral formulation, and we have a first order approach, the Hilbert-space formulation, with a first order time evolution equation for the wave function or the density matrix. But we don't have anything like the physical picture, the analog of having phenomena happening according to equations of motion. The claim is that this missing piece consists of generalized stochastic systems. So systems that are going to be a lot like classical systems, but where their laws are not going to be second order deterministic differential equations, but stochastic laws. And the claim is that these give quantum theory a physical nature that could make it more commensurable with scientific practice, in which we can say that phenomena, broadly speaking, are in fact happening, and measurements are only one kind of phenomena that happen. So in this talk, I'm going to present a new formulation of quantum theory in terms of a correspondence with stochastic processes. Why wasn't this formulation discovered before? What's our unfair advantage today? Well, possibly because this formulation depends on concepts that were just not available back in the 1920s or 30s, and some of them weren't even widely known until the 2000s. These include stochastic matrices. Stochastic matrices were introduced by Markov all the way back in 1906, but if you do a Google Ngram viewer search, you'll see that they weren't in wide use until the 1950s, which is decades after quantum theory as we know it, textbook quantum theory, was fully solidified. I'll also be using a concept called a unistochastic matrix. Now, this was actually introduced by a mathematician, Alfred Horn, in 1954. He was not thinking about stochastic processes. He was an analyst, and he was studying linear algebra, and he just thought these were interesting mathematical constructs. Originally, he called these orthostochastic matrices. Eventually, another mathematician in 1989, Thomson, introduced this somewhat more precise term, unistochastic, to refer to them, and I'll explain what these things are. But these are of relatively recent vintage. And finally, most recently, Ignacio Chirac and Mikhail Wolf introduced the concept of an indivisible process. They were thinking in terms of quantum processes, quantum channels in particular. But the idea of an indivisible process is a broader idea. And it was really only in the last 2 or 3 years, remarkably, that people began to apply them in the classical case. These turn out to be a distinct way to generalize Markov processes. So when someone says non-Markovian now, they don't necessarily just mean non-Markovian in the sense of systems with memory. There's a distinct way to generalize a Markov process, one that people weren't aware of before. And this is called an indivisible process, and I'll explain what it is shortly. So the new formulation I'm going to be presenting is based on the following theorem. And this theorem is proved in the first of those 2 papers that I showed at the beginning. Every generalized stochastic system, and I'll define what that is in a moment, can be regarded as a subsystem of a unistochastic system, which I'll also define in a moment. And you combine this with the fact that a unitarily evolving quantum system can be regarded as a unistochastic system in disguise. This will imply a precise stochastic quantum correspondence. Now, again, I'm going to need to define what these terms mean. Fortunately, they're remarkably simple. They're not mathematically complicated to define at all. They're just new. I'll also need to write down an explicit dictionary that will translate between stochastic systems and quantum systems. I will give you the translation, the dictionary between the two. So if you want a pithy one-liner or a takeaway from this talk, the claim here is the universe is in some configuration, evolving along a trajectory, governed or described by a stochastic process, and more precisely by an indivisible stochastic process. And again, I'll explain exactly what that means in a moment, but it's not hard, it's not complicated. For now, just note that outside the deterministic case, unistochastic means indivisible, and I'll define all of this, and it will all be intuitive. Just give me a moment. The path ahead will be to construct the usual Hilbert-space formulation from this via a set of mathematical definitions, identities, and theorems. I'm not going to need to reify or augment any of the Hilbert-space ingredients. I'm not going to have to treat any of them as being metaphysically real or adding to them or arguing for any speculative metaphysical hypotheses about parallel universes or emergence or anything like that. But in particular, this talk, by the end of it, you should feel a little bit guilty about telling students that an atom can be literally in two places at once, or cats can be alive and dead. That won't be a part of this picture at all. We'll need to begin by reviewing how standalone probabilities, joint probabilities, conditional probabilities, and marginalization work. So just super quick, P of E probability, standalone probability of some proposition E, P of F, same for F. P of E and F is the joint probability. P of E vertical line, which should be read as given. P of E given F is the conditional probability V given F. We have this usual factorization that, starts off Bayes' theorem that the joint probability of E and F is given by the conditional probability of E given F times the standalone probability of F. And we have marginalization, right? If you sum over F in the joint probabilities, you get the standalone probability for E. And if I plug in this factorization, I get this formula here. This formula will be important. It says that the standalone probability for proposition E can be expressed as the conditional probability V given F times the standalone probability for F summed over F. Okay, and this all just follows from the basic structure of how joint and conditional probabilities work and how they're related to standalone probabilities. This is all dictated by just the nature of how probability works. Okay, so that will be important to remember. Now I'm going to start with an invitation. It's good to have a nice picture in mind. This will be a guiding picture for our work ahead. So to be clear, this talk will not be limited to any specific kind of quantum system. It'll be very general. I'm not even going to be sticking to non-relativistic particles. But a well-known single particle thought experiment will provide a good invitation to what we're going to do and what you should keep your eyes out for. So recall the double slit experiment. One imagines sending particles one at a time toward a wall with two slits and observing where the particle arrives on the screen. Now, people slyly assume this one particle at a time, criterion, and they'll say they're doing it just, because they don't want you to think maybe that you have two particles, the particles are bumping into each other, but that's not why they're doing it. They're assuming one particle at a time because this ensures that we have a 3D configuration space, that our waves move in 3D space, and this confuses students and makes them think that wave functions actually move around in 3D space. Of course, if you did it with two particles, your wave functions would live in 6D space. And then the idea that really this is about waves moving in 3D space would seem maybe like it doesn't fit. I think we should be honest and be clear about this. Wave functions don't live in 3D space. Let's draw this picture here. Okay, so here's our particle coming in, our two slits. We'll assume the slits are close together. Let's let A denote in a broad way the starting conditions, B to denote which slit the particle goes through, and C where the particle lands. So we have these three random variables or propositions. Now, the usual classical assumption, made when people say, oh, we're going to treat this classically, is they assume that you have the following relationship between conditional probabilities, that the conditional probability for the particle to land at a landing site C, given its initial conditions A, can be expressed as a sum over which hole it goes through of the conditional probability that it lands at landing site C conditioned on going through hole B, multiplied by the conditional probability that it will go through hole B given its initial conditions A. Note, this formula does not follow from that formula I told you to remember before. This is not an example of that formula. This bakes in an assumption. It assumes that we have a Markov assumption, that basically we can restart the evolution at the holes and forget about the past. And this does not follow from the basic structure of probability theory. Now, I should say that this is usually not written down explicitly, but it's between the lines if you read any treatment of the two-slit experiment and how it's supposed to work in the classical case. This is an implicit assumption behind those approaches.
Quick question, Jacob.
Yes, please.
Someone asked, is this similar to the IID assumptions in Bell's theorem?
Oh, so I'm not going to have time to talk in detail about Bell's theorem in the main talk, but hang on to that question. If you'd like to talk about it after, I would be very happy to talk about it.
Okay, thanks.
But it's not connected to the IID assumption, no.
Okay.
Okay, so, and actually, by the way, people often treat the classical case as deterministic, but deterministic evolution is inherently Markov. Here I'm being even more general. I'm bending over backward to accommodate the possibility that you could even be doing this probabilistically, but this is still an implicit assumption. If you make this assumption, then you find over many repetitions that you get a histogram that looks like this. You combine them and you get this blend here, and this is supposed to be the classical prediction. And indeed, this does match observations for when you do the experiment with macroscopic particles like stones. For an electron or photon, one observes instead what looks like an interference pattern. Does this mean that the particle is really a Schrodinger wave, or the particle somehow goes through both slits? Well, it's not clear. The textbook theory is not clear about this. If we insist on thinking about waves, the answer is definitely no. The waves definitely do not go through both slits, for the simple reason the waves don't live in physical space at all. They live in configuration space. Again, if I were to do this experiment with two particles, the waves would live in 6-dimensional space, and I don't even know where the holes are in 6-dimensional space, right? So this picture that waves are really moving in 3D space isn't even the correct picture, even if you wanted to take it that way. Schrodinger, by the way, knew all this. He wrote about all this in his original papers on wave mechanics, and he was deeply confused about it, and I'll have more to say about that later. Anyway, but the upshot is we're going to show that one can account for this pattern without waves, merely by allowing the dynamics to be non-Markovian or indivisible. We're not going to make that Markov assumption that I said people typically make. That is, we're not going to assume this equality. And in fact, we're going to compute the difference between the left-hand side and the right-hand side. And I'm going to show explicitly that that difference exactly gives you the interference pattern with no assumption of waves. Okay, I need to briefly review the Hamiltonian formulation for a classical system, right? This will be a good motivation for what I'm about to do. So if we're modeling a classical system, like it could be a Newtonian system, the system we assume has a configuration, which I'll label with I, and it has some list of possible values, 1 through n, and some set C called the configuration space, which could be infinite. We, typically will coordinatize this configuration space using degrees of freedom, real value degrees of freedom, Q1 through Qn. That's little n here. This is a different little n. It's just how many coordinates I need to identify uniquely each configuration. At the level of dynamics, we will assume deterministic laws. Generally, we assume second order and time differential equations as our laws. And then we write down the Lagrangian formulation, and then we write down the Hamiltonian formulation. The Hamiltonian formulation is phrased at the level of phase spaces, where we double the number of variables. We include coordinates and their corresponding canonical momenta. Note, the reason we use canonical momenta and we can stop there is because the equations are second order in time. You can take n second order in time differential equations and turn them into 2n first order in time differential equations. And that's essentially what you do, right? The reason why we single out the momentum and treat them on the similar footing as the Q's, and the reason we do this at all is because we're turning second order equations into first order equations in terms of the Q's and P's. The dynamics is then written explicitly as first order equations, Hamilton's equations of motion. So there's no magical reason why P's are on the same footing as Q's, except that it's given by the dynamics. The dynamics is what singles out this approach and this definition of the phase space. And then we can go on and introduce rho, a probability distribution on phase space, and show that it evolves according to the Liouville equation. The time derivative, the partial time derivative of the probability distribution on phase space is given by minus the Poisson bracket of the classical Hamiltonian with rho, with the phase space distribution. Right, so this is how you could think about setting up Hamiltonian mechanics and doing a statistical treatment of it. We're going to set up a very analogous thing now. At the level of kinematics, a generalized stochastic system has the same basic story as in the classical case. It's got configurations that you can mentally combine into a configuration space. The dynamics is where things are going to be different. Now we're going to assume the dynamics is more general. We're going to allow for more general dynamics. We're going to allow the dynamics to be stochastic. We're going to say that if the system is in its jth configuration at time 0, then we have the following conditional probability, P of I at t given j at 0 for the system to be in its ith configuration at the time t. This is, strictly speaking, more general than deterministic evolution, and we're going to be very general about this. I'm going to put no constraints on this except the ones that are dictated by probability theory. And so this dynamics generalizes what we do in the classical case. Now, we're not going to end up with phase space because we don't have second-order deterministic differential equations anymore. We're going to end up with something different. And the claim is what we're going to end up with is quantum mechanics, right? So remarkably, and this is what the theorem shows, we're going to end up with quantum theory from this. Quantum theory is the analytical mechanics of this kind of a system. I should make clear that this approach is not connected with earlier stochastic approaches to quantum theory by Fritz Bopp in the 40s, Imre Fenyes in the 50s, and Edward Nelson in the 60s. This is really a completely different approach. It also has nothing to do with stochastic collapse approaches, which take the wave function to be a physical thing. This has nothing to do with those either. This is really very simple. Just a system with configurations that we put into configuration space, just like classically, but with a more general set of laws for how the configuration changes with time. All right, let P1 through Pn at 0 be standalone probabilities at t equals 0. Again, this is just dictated by the rules of probability theory. They're non-negative and sum to 1. Same at time t. They're non-negative and they sum to 1. These are all things that hopefully people are familiar with. These standalone probabilities are linearly related by the conditional probabilities that define the dynamics according to this marginalization formula. And this is directly the marginalization formula I gave at the beginning. This is how conditional probabilities connect standalone probabilities in the general case. It's linear. It's a linear relationship. You can freely adjust the initial probabilities at 0. In particular, the linearity of quantum evolution, which is just an axiom in the usual textbook Dirac-Van-Neumann approach, will descend from this basic structure of how probabilities work. It's no longer an assumption, it's something that follows because I'll show that it arises basically from this formula. Now we can naturally express this formula in matrix notation. I'm just taking that formula and writing it as matrices, n by 1 matrix, n by 1 matrix, and then the conditional probabilities form an n by n matrix. If I define gamma, capital gamma, to be that matrix, then our formula relating the standalone probabilities at 0 and at t can be written in this very succinct way. Gamma of t consists of conditional probabilities. So because of the structure of how probability works, its entries are non-negative and its columns sum to 1. That identifies it as a column stochastic matrix. The sum here is down each column. So gamma of t here is called the system's transition matrix. I'm going to stay as general as possible here. I'm not going to assume we have a Markov process. In particular, I'm not going to assume something like a discrete time Markov chain. I'm not going to assume that you break time up into discrete time steps and that the evolution over each time step is just multiplying repeatedly by some constant stochastic matrix. I will not be assuming that. A less well-known approximation is divisibility. So this is this idea that was introduced only a couple of years ago.
Just a quick question here, Jacob.
Yes, please.
Someone asks if you're assuming that the stochastic dynamic matrix gamma is reversible for unitary processes, and if so, what restrictions that place on the matrix?
That's an excellent question. I'm going to connect it up with unitary processes very shortly, and then I'll address that question explicitly.
Okay, good. You keep like having backup for all.
They're all great questions, but we'll get there.
Yeah. Cool.
Okay, so this is a less well-known approximation. It's the statement that if you give me an intermediate time t prime between 0 and t, that I can break up the stochastic matrix in the following way. I have gamma of t prime, which evolves us from 0 to t prime. I have gamma of t, which evolves us from 0 to t. And if this is a divisible process, then there will exist a genuine column stochastic matrix, non-negative entries, column sum to 1, gamma of t from t prime. It's the purple matrix. I haven't supplied that, but if your system is divisible, then that should exist. And it should connect the evolution in this way. You can evolve from 0 to t prime and then use this purple matrix to evolve from t prime to t. But I will not assume that. I will not assume that exists. And it's easy to come up with examples where such a matrix simply doesn't exist. Here's a perfectly smooth analytic case. This is a 2x2 transition matrix. You can show explicitly it's non-Markovian and indivisible. There is no purple matrix that connects times t prime to times t. You can just verify this. This is done in detail in the second paper. Here's another example. This one's periodic, also analytic, but this one exhibits periodicity. And indeed, non-Markovian indivisible transition matrices like these are the generic case. You have to actually impose additional assumptions to make a transition matrix be Markovian and divisible. I will not assume that. I'm going to be general. So here's the crux of it. This is this new formula. This is the basic dictionary. It's this mathematical identity. You can take that stochastic matrix I introduced, gamma, take its ijth entry, and express it in the following way. Now, let me explain the ingredients of this formula. The brown matrix here, theta, that's an n by n complex valued matrix. It's not unique. And that's actually important. It's not uniquely defined by this formula. You can use any matrix at all that satisfies this formula, and there are infinitely many choices. The Pi and Pj are very simple. They're just projection matrices, and they're the simplest kind. Each is a matrix of zeros with a single one in its ith entry for Pi or its jth entry for Pj. If you put things together in this way and take the trace, then for a suitable choice of theta, you will get back gamma, right? And this is a mathematical entity. It's not a postulate. You define theta by this relationship, and theta is not uniquely defined. You're allowed to use any theta you want, and there's a large number of thetas you could use for which this formula is true. This centrally important new result is a dictionary. It translates between generalized stochastic systems, that's on the left, that's the gamma matrix, and Hilbert-space ingredients. That traces over a Hilbert space, and I'll explain in a bit what all these formulas mean. That's what's on the right. It establishes a precise stochastic quantum correspondence, and it lets you translate between statements for the generalized stochastic system, which is really what's going on, the fundamental physical picture, and this mathematical representation as a Hilbert space. And the argument is we can get every single quantum system this way. And every quantum system can be interpreted as a generalized stochastic system by reading the correspondence backward. Now let me make the connection to unitary evolution. So the theorem proved in the first paper shows that if need be, slightly enlarging the system, but you don't necessarily need to, but in some cases you may, you can always assume that gamma is a unistochastic matrix. Unistochastic means that its entries, gamma ij, at each time t, are individually the mod squareds of the entries of a unitary matrix U. Okay? U here is unitary. So this is not the whole matrix being multiplied by itself. I'm saying that literally each entry of gamma, each of its individual entries is itself the mod squared of the entry of another n by n matrix U, and that matrix is unitary. So that theta matrix I said before, which was highly non-unique, if your system is unistochastic, if gamma is unistochastic, then you can pick theta to be unitary. And again, the theorem establishes that if need be, making your system a little bit bigger, you can always assume that theta is unitary. Okay, so now, instead of that general theta matrix, we can assume that U is a unitary matrix. Now, you might wonder, does this mean that gamma is invertible? No, it does not. That relationship between gamma and U does not commute with matrix multiplication. So the fact that U is invertible does not mean gamma is. Anyway, generalized stochastic system with this feature will be called a unistochastic system. I would just mean that its stochastic matrix, its matrix of conditional probabilities that define its laws, are expressible in terms of a unitary. Then we say the system is unistochastic. And indeed, this will serve to define what we mean by a closed system. So as claimed, every generalized stochastic system can be regarded as a subsystem of a more narrow kind of generalized stochastic system, unistochastic systems. Okay, well, I can take this unitary that I now have in my hands, I can take my initial standalone probabilities, p's i's of 0, make them the diagonal entries of an n by n matrix, sandwich that diagonal matrix between U and U dagger, and use it to define a row of T, which will serve as a density matrix. In the rank 1 case, I can split that up. Outside the rank 1 case, I may have to have a linear combination of unit vectors, but I can always break it up and express things in terms of these unit vectors psi if I want. If we let A of t now be a random variable, on the generalized stochastic systems, this is just a totally boring random variable. It's just a list of magnitudes or values labeled by which configuration the system is in, I1 through n, and possibly explicitly depending on the time t. Well, I can take the standard formula for its expectation value, the weighted sum of its possible values ai of t weighted by the probabilities pi of t. And it's very easy now to show that this is expressible as trace of a certain product, a product of a matrix A of t times rho of t that I'll define in just a moment. In the rank 1 case, of course, this descends down to the familiar formula for how we compute expectation values. Here, the matrix representing a random variable is just basically a diagonal matrix. It's a diagonal matrix with the entries along the diagonal, giving the possible magnitudes, the spectrum of magnitudes. Okay, so this is a self-adjoint operator. It is diagonal. So immediately we can already begin computing expectation values of diagonal observables, random variables, right away, right? Just from what we already have so far. I will get to more general observables in a moment. We'll be able to get all of them. But at this point, we can already get the diagonal part of the diagonal subalgebra of the algebra of observables. Okay. Well, assuming U of t...
Jacob, just a question.
Yes, please.
Yeah, so this is from 1 or 2 slides previously, but someone in the audience asks, in doing these constructions, do you need to assume that the Hilbert space is complex?
Oh, I'll get to the complexity of the Hilbert space in a moment. Yes, that's also in the slides. These are all great questions, but I'll get to them. Yes.
Cool. Thanks.
I'll be able to explain where the complex numbers come from. Yes. So stay tuned. Excellent question. Okay. So assuming U is a smooth function of time, we are physicists or philosophers. I guess it depends on what hat one is wearing. But assuming that U of t is a smooth function of time, the rest is now going to be inevitable. You can introduce now a generator for this time evolution in the standard way. I here is introduced only to ensure that H is self-adjoint. If you insist on having a self-adjoint Hamiltonian, you do need I here. If you don't care about that, then you don't need the I, but it's convenient to introduce it. H bar is just for units. If you wanted to work without units, you wouldn't have to worry about the H bar. And then we can compute the time derivatives of the various objects we've introduced. That state vector psi will obey the Schrodinger equation. Rho will obey the von Neumann equation. You can go ahead and define Heisenberg picture versions of your observables. They obey the Heisenberg equation. You can check that the Ehrenfest equation holds. Note, H of t, rho of t, and Heisenberg picture versions of our observables will generically be non-diagonal. And also, those brackets are not Poisson brackets. They're actual commutators of non-commuting matrices. Notice the von Neumann equation looks just like the Liouville equation. Of course, people probably already know that. But now actually it's doing the same, it's playing actually the same role. It's capturing our statistical information of an underlying physics, the way it did in Hamiltonian mechanics. Let's do a simple example to make clear why unistochastic systems don't have to always be an exotic idea. Consider a discrete dynamical system whose dynamics is based on a permutation matrix. So that is, we're going to assume we have like a deterministic system. And all that happens is every time step delta t, we permute which configuration the system is in. And after n time steps, we just do n permutations. So it's like a homogeneous in time evolution law. The configuration simply hops around between different possible configurations, as a permutation transformation. It's basically a discretized version of classical dynamics. Well, every permutation matrix is unitary and unistochastic. And there's more. Because the permutation matrix that defines each individual time step's evolution, because it's unitary, its roots exist and are also unitary. So I can set it to the power t over delta t, where t is treated as a smooth parameter and delta t is our time step. This exists, and you can define it by diagonalizing, in which case all the diagonal entries of the diagonalized version of sigma will be phases, multiply the phases by t over delta t, and then undiagonalize. You can check it all works out perfectly nicely, and the result is still unitary. So this thing has roots that are also unitary, and I can treat those roots as a function of t. And then you can take the square of the entries to define a manifestly unistochastic transition map. And this gives you a smoothly time-dependent unistochastic system that smoothly interpolates between the discrete time steps. It turns our discrete deterministic process into a stochastic process, where at every discrete time step, it looks deterministic, but you have smooth interpolation between the time steps now. And you can actually show the system has a Hamiltonian, it has a Schrodinger equation, it looks just like a quantum system. Now let me get to the complex numbers. So for n bigger than 2, so for a system with more than 2 configurations, an n by n unistochastic matrix will not generally be orthostochastic. So today, orthostochastic means unistochastic, but where you can use a real orthogonal matrix instead of a unitary. For n bigger than 2, you cannot generally do that. You can't take advantage of the unistochasticity without the complex numbers. Okay, so the complex numbers, or an algebraic construct isomorphic to them, will be necessary to model general systems in this framework. But look, the whole Hilbert-space picture is fictitious, just like the action functional or the Hamilton's principal function. It's just mathematics. And it's incredibly convenient to use complex numbers when you model that mathematically. With the complex numbers, we can apply the spectral theorem. We have symmetry generators, Hamiltonians, energy eigenvalues, stationary states, the Schrodinger equation. It makes it way easier to derive the uncertainty principle. Because the mathematical picture is make-believe, we can put complex numbers in there if it makes the mathematics easier. But the point is, even if we didn't want to do it, even if we, for whatever reason, didn't want to do it, the need to represent things in general with unistochastic matrices would require it. Actually, this is a nice opportunity to mention that even in textbook quantum theory, the fact that you need to introduce a K operator that implements complex conjugation to manage time reversal. So time reversal transformations involve anti-unitary operators that involve this K operator K. You need these in order to implement time reversal. This complex operator, complex conjugation operator K, it complex conjugates things. If you do it twice, you get nothing. It squares to 1. By definition, it anti-commutes with I because it complex conjugates. And you can check that I, the complex, imaginary unit, K, the operator that complex conjugates, and IK generate a Clifford algebra called the pseudoquaternions. In a sense, textbook quantum theory is really based on the pseudoquaternions, not just on the complex numbers. That's just an interesting aside. When everyone says quantum mechanics is based on the complex numbers, why? I say, actually, it's not just the complex numbers. Technically, it's actually based on the pseudoquaternions. Now, at this point, you might still wonder whether you can empirically access more than just diagonal observables. The ones that correspond, to random variables on the original generalized stochastic system, these correspond to diagonal self-adjoint operators, like I showed before. Bell would have called these things beables, not just observables, but the way a system can be, like ontologically speaking. Don't all the observables of a genuine quantum system form a non-commutative algebra? And what about supposedly signature or hallmark empirical features of quantum theory, like interference and entanglement? Not to worry, I will show how all the rest naturally appear. In particular, I will show that non-diagonal observables, as well as interference, are emergent patterns in the dynamics. The observables, the non-diagonal observables, the ones that don't have a transparent meaning at the level of the configuration space, those will be emergent patterns that I'm going to call emergibles. So that is, the set of observables for a quantum system includes beables, which make sense, have a transparent meaning at the level of the system's configuration space. These are the things that have a particular value depending on the system's configuration, and maybe also depending on the time. And emergibles, things that show up when you do measurements. And I'll show exactly how this works. Let me start with interference. So let's consider a closed system, and we're going to use unitarity to define a relative time evolution operator. So I have a unitary time evolution operator u of t. I can take its adjoint. I can evaluate the adjoint at another time t prime. I can multiply them, and I can define this purple operator u of t from t prime. And if I rearrange this, I get the following composition law. So I can evolve from 0 to t prime using u of t prime. I can evolve then from t prime to t using this purple matrix, u of t from t prime, and then it's the same thing as if I evolve from 0 to t. Now, you might look at this and go, wait a second, didn't I say that in general you couldn't do this? Well, you can't, at least not the level of gamma, but you can in terms of u. Remember, u and gamma are related by this sort of square property, right, of squaring the entries. If I take the entries of this purple matrix u individually and square them, I will get a unistochastic matrix gamma of ij that I could try to think of as the matrix that evolves from t prime to t. And so you might wonder, does this serve in the right role? Does this let me do stochastic evolution from t prime to t? And the answer is it does not. In general, this purple matrix does not work. It does not give you this evolution. It works for u, but remember, u is related to gamma by squaring its individual entries. That does not commute with matrix multiplication. And it means that we will not get that composition law for gamma itself. Indeed, if we compute the difference between the left-hand side and the right-hand side, we get this formula here. This formula is the set of cross terms, and these cross terms are identical to the formula for interference. This is literally the formula for quantum mechanical interference, which we see is merely discrepancy between the actual indivisible dynamics and an erroneous assumption of a nearest approximate divisible dynamics. So if you assume that dynamics was Markovian or divisible, you'll get the wrong answer. And how wrong your answer will be is literally exactly the mathematical formula for interference. Notice we didn't need to invoke Schrodinger waves here, like I said. And from this perspective, it was an unfortunate accident of history that so many early examples of quantum mechanical interference, like in the double slit experiment, resembled wave interference in 3D. As I said, wave functions don't usually even live in 3D space. And we should stop telling students that, well, insinuating that they do, even though we know they don't. Schrodinger, by the way, pointed this out immediately in his 1926 paper, that his wave functions lived in configuration space, and he was very confused about this and tried to embrace it. Einstein hated the idea. In fact, one of the few things that Einstein and Heisenberg agreed on in 1926 was they both disliked the idea of taking waves in configuration space seriously. You probably all remember the letter that Einstein wrote to Max Born in 1926, arguing that God does not play dice with the universe. But literally the next statement in that letter, the next sentence is Einstein saying that he couldn't believe that there were really waves in 3 n-dimensional configuration space, that was the seed of reality. He couldn't take it seriously, and he didn't like the idea. Okay. N particles in 3D have a configuration space of dimension 3n. And of course, there are more abstract systems like qubits that don't even have a continuous configuration space at all. But now we finally have a framework that's general enough that we can explain in theoretical grounds where and under what circumstances the Markov approximation, irrelevance of past states, often works so well in applications. And this will be a good step toward explaining how we do measurements of more general observables. So consider a composite system, a subject and environment. And by this, I just mean in the classical sense. It's got an overall set of configurations. Each configuration is a pair of a configuration for the subject system and the environment. Suppose that for each configuration I of the subject system, the environment has a corresponding configuration E of I that depends on the configuration of the subject system. We think of this as the environment. It has done a reading. Its configuration is dependent upon the configuration of the subject system. And suppose the overall transition matrix describing the stochastic evolution has somehow yielded the following relationship, which is just to say that it's produced a simple classical correlation. The joint probability for subject, system, and environment breaks up in the following way. It's given by an arbitrary probability distribution over the configurations of the subject system at the time t prime, and then the configuration of the environment must, with unit probability, be in its configuration in which it's done that reading. And this is just classical correlation. Okay? And assume, at least for a brief moment, that there are no further interactions. Maybe there'll be more interactions later, but at least for a moment, the interactions, there's some short period of time in which the systems behave independently. Without that, we can't even talk about what's going on with either of the systems individually. This is an assumption we always make classically anyway. Okay, now if we marginalize over the environment, this is classical marginalization now. I'm doing it at a level of stochastic dynamics. I'm not even mentioning quantum theory here. We just marginalize over the configuration of the environment. We now get the following rule with this purple matrix showing up, connecting the probabilities at t prime and the probabilities at t. So now we do have a purple matrix that connects the time evolution from t prime to t. That is, due to the correlating interaction in the environment, there is a new division event at t prime. This plays the role of a new t equals 0 and lets the evolution restart. Now, we expect division events to be ubiquitous for open systems and noisy eavesdropping environments, an environment that's constantly checking in on the configuration of the system. And this gives a first principles explanation for why the Markov approximation often works so well on macroscopic scales. We can really put mathematical teeth behind the idea that correlations are leaking out into the environment. We can actually model the whole thing without assuming the Markov approximation from the beginning. It's easy to show, by the way, that at that time t prime, the moment when the environment has done its reading, that if you compute the subject system's reduced density matrix in the Hilbert-space formulation, well, then the density matrix will become momentarily diagonal, and this is exactly decoherence. So we learn, in particular, that the off-diagonal entries in the density matrix, the coherences, which, by the way, correspond to superpositions and wave functions, are merely a mathematical artifact of indivisible, roughly speaking, non-Markovian dynamics. Those off-diagonal entries in the density matrix have a meaning. They're encoding the indivisibility, right? And decoherence, the washing of those coherences away, like sweeping away cobwebs, is just what the mundane leakage of correlations in the environment looks like when you see it through the lens of the Hilbert-space formulation. Let me talk a little bit of entanglement, and then we'll get to measurements, and that will be the end of the talk. So even in classical deterministic physics, during an interaction, while interactions are happening between two systems, we don't have factorizing dynamics, right? So if you have two systems in the middle of interacting, the potential energy, say classically, speaking classically, like a Newtonian case, doesn't factorize into two pieces, right? Given two subsystems A and B, suppose they're not interacting with each other from time t equals 0 up until just before some later time t prime. Well, if they're not interacting with each other and they're independent, then the overall stochastic matrix of the system will factorize. This is easy to check, right? This is just follows from the assumption that they're evolving independently up until the time t prime. However, a transition matrix like gamma encodes cumulative statistical information. So if there's an interaction at t after t prime, then at least until another division event, the overall stochastic matrix of the composite system will fail to factorize. And there's nothing that will make it refactorize even as you wait, because it's including all the cumulative statistical information. And if at any point in the past, at that time t, there was an interaction, we will just continue to fail to have factorization basically indefinitely. And this already looks like entanglement. But now assume that at an even later time t double prime, say the environment comes in and reads one of the two subsystems. Then we get a new division event at t double prime. The evolution divides. We can now introduce this new purple matrix that goes from t double prime to later times t. And if the systems by this point were no longer near each other, no longer interacting, well, then that purple matrix will factorize into two pieces of the two systems. They'll have their own independent dynamics again, and we get the breakdown and entanglement. Decoherence causes a breakdown and entanglement. This is how it all shows up in this stochastic picture. So this is entanglement written without Hilbert spaces. This is entanglement written directly in terms of what's going on with underlying stochastic systems. Now I can finally talk about measurements. Let's consider a general self-adjoint operator. Okay? If it's diagonal, this would be one of our variables, random variables with a transparent meaning at the level of the configuration space, with values that just depend on what configuration the system is in and time. But if non-diagonal, then this doesn't have such a transparent meaning. Let's write down this self-adjoint operator. We'll write down its spectral decomposition in terms of eigenvalues A sub alpha and projectors P sub alpha. These projectors will generically be non-diagonal as well. They're labeled by some label alpha. They form some new projection value measure. And these real eigenvalues have no obvious meaning yet. To set up a measuring process, I'm just going to generalize what we did when we were studying decoherence by the environment. I'm going to take a piece of the environment and call it a measuring device. And I'm going to have an explicit definition of a measuring device. I'm going to define exactly what it is. It's a system with outcome configurations. It's got configurations of its own, and those configurations have labels that correspond to labels alpha. There's an environment that couples to the measuring device, and there has to be an overall transition matrix, an overall stochastic dynamics that implements a certain kind of a process. This overall stochastic matrix, gamma SDE, will be defined in analogy with what we did for the environmental decoherence case. I'm not going to do any gerrymandering or additive fine-tuning. I'm not going to like carefully design a bespoke gamma to make all this work. I'm literally just going to take the usual unitary time evolution operator we use to model a textbook von Neumann measurement, and I'm going to square its entries and use that to define a stochastic matrix. So for example, this is a very simple example of an idealized unitary that would implement a von Neumann measurement. Here we have the eigenprojectors of A, and here we have unitary transformations that align the configuration, configurations of the measuring device and the environment to get the reading. Again, this is just textbook quantum theory, and I'm going to define gamma SDE at the top. It's going to be the unistochastic matrix for which this is its corresponding unitary time evolution operator. So no special work here, just literally taking this from the textbooks. And the results come out exactly right. You let the system evolve stochastically according to the stochastic dynamics. What you find is that the probability for the measuring device to end up in one of its outcome configurations, d of alpha prime, at the time t prime at the end of the measurement, is given exactly by the absolute value squared of the subject system's wave function in the observable's eigenbasis. This is exactly the Born rule. So just letting the stochastic evolution happen, the measuring device will end up in its appropriate configuration with a probability exactly predicted by the Born rule, right? But the whole thing is just some stochastic process evolving around. And the fact that the measuring device ends up here is just one example of a more general kind of stochastic phenomenon taking place. Moreover, we can condition on that measuring result, because these are just probabilities. We can condition on it, and we get a formula that looks a lot like the Born rule, but with an updated density matrix that's given by wave function collapse. Okay. So that is, because these are just probabilities at this level, we can condition on the result of the measuring device. And then all future predictions we make about the subject system are given by replacing the subject system's original density matrix with a collapsed density matrix. So collapse is now just the Hilbert-space version of conditionalization. All right, this is my concluding slide. What we've been able to do is explain where the linearity, unitarity, and Hilbert spaces all come from. Complex numbers, non-commutative algebras, they're no longer posits. We can explain why we use the complex numbers in quantum theory. We deflate some folklore. Superposition is no longer literal. Sorry to the many worlders out there. Measuring devices are now ordinary systems. I can give you a definition of what they are. They have to have enough configurations. They have to have the necessary dynamics and an environment to ensure robust division events. So there's arguably no measurement problem in this picture anymore. We get a clearer interpretation of the insertion principle. I didn't have time to talk about that, unfortunately, or the no-go theorems. And again, if there are questions, I can talk about the no-go theorems, including Bell's theorem, which, by the way, and again, if people have questions, I can explain why this does not give a more non-local theory than textbook quantum theory already. And you can show it meshes rather nicely with special relativity, in which times are replaced by space-like temporal hypersurfaces. There are some interesting open directions, open questions and future directions here. Be interesting to think about how to generalize dynamical symmetries in such a theory. It gives you a new way to think about dynamical symmetries. There are some implications for old problems in statistical mechanics. Be interesting to explore ramifications for algebra first approaches to quantum theory, including the famous problem of unitarily inequivalent representations of C-star algebras. I'm particularly interested in this question. Can we use this as a platform for developing new algorithms for simulating non-Markovian and indivisible real-world systems? Big macroscopic, seemingly classical systems, but maybe non-Markovian systems on quantum hardware. It'd be interesting to see what it would look like to construct explicit models for various important kinds of quantum systems in this framework, in condensed matter, quantum field theories, and see if this more physical picture gives us new insight and new intuition about how these systems behave. But this is also a good place for maybe building self-consistent generalizations of quantum theory that don't rely on Hilbert spaces at all. And that could have some potential implications for quantum gravity. So I want to conclude with the following quotation. Nevertheless, there can be no fundamental objection to the idea of a stochastic theory, except on grounds of a naked prejudice for determinism. The question of determinism or indeterminism in nature is obviously forever undecidable in physics, since for any current deterministic or probabilistic theory, one could always postulate that a refinement of a theory would disclose a probabilistic or respectively deterministic substructure, and that the theory is to be explained in terms of the refined theory on the basis of the law of large numbers, or respectively ignorance of hidden variables. However, it is quite another matter to object to a mixture of the two, where the probabilistic processes occur only with acts of observation. I'm just curious if anyone knows who wrote this. Anyone want to make a guess?
I feel I have to make a guess now. But can you give us a hint of how recent?
It was said in the 1950s. It was written in 1956 by someone at Princeton.
Okay. Oh, then it's Einstein.
Unfortunately, no. Einstein was dead a year by this point.
Okay. Then tell me.
This was said by Hugh Everett III in his unsubmitted long-form PhD dissertation, The Theory of the Universal Wave Function. Remarkably, Everett talks about stochastic approaches to quantum theory in that long-form dissertation. He actually makes reference specifically to Bopp's stochastic approach, which, like I said, is different from mine, but similar a little bit in spirit. And Everett actually has no objections to it. This is why he says this comment. But he does say he'd like to find something deterministic just to see if it's possible, and that's part of his motivation for many worlds interpretation. Anyway, that's the end of my talk. Thank you very much. Happy to take questions.
Thanks,
I
Jacob.
have a simple question.
Yes, Crispin, go ahead.
So if you have a parabolic quantum well and you have a single particle in the ground state, how does this interpretation describe that? So, for example, in Bohm, that will be described as a particle that is literally stationary, or in a Copenhagen interpretation, you would say, well, you have you have your wave function, a probability of finding the particle at a certain position is given by the mod squared of the wave function. How in your theory would you describe that ground state?
Yeah. So suppose we have a particle. So I take this to assume we have a particle that's in a quantum simple harmonic oscillator, right? It's in a parabolic potential like in a harmonic oscillator.
In its ground state.
Exactly.
State,
You're right. So in Bohmian mechanics, there's some probability distribution over where the particle can be. And the quantum potential kind of keeps the particle hovering at some particular point that you don't know what it is, right? In Bohmian mechanics, we have what looks kind of like deterministic evolution. Now, I didn't talk about Bohmian mechanics in this talk. Bohmian mechanics is in some ways a little bit like this construction, but much more complicated because of the insistence on determinism. And also Bohmian mechanics is famously very difficult to generalize beyond systems of finitely many non-relativistic particles. So what happens in this picture? Well, there's still a probability distribution, right? So you could still ask where the particle is at any given moment in time t. These particles in the ground state, you can say, well, where is the particle? Where is the particle? Where is its location? What the wave function is doing, it's not a physical object. Wave function is not a physical thing. But the wave function does tell you what that probability distribution is of where you'll find the particle. So the particle is somewhere in the well. I don't know where it is. And that's about all you can say. The stochastic matrix in this case doesn't change that probability distribution. So the particle is located somewhere, and I don't know what it's doing. And that's the answer. So you don't get any information about the particle's detailed trajectory. We don't get that information. Okay. It's there and it's doing something, but I don't have laws that tell me what it's doing.
Okay, so that in contrast to Bohm, where you do know that it's not moving and it is at a location. Correct. In what you're saying.
We don't know whether it's moving or not. We don't have laws that give us that information. The dynamics in this picture is sparse. We can say many things. And if you have a system that's in strong contact with an eavesdropping environment, you can piece those things together and actually make detailed predictions about what's going on with the trajectory of the system. But for a highly isolated system, isolated from its environment, like a particle kept isolated in a well, we can say probabilistically where the particle is, but we don't have an ability to write down detailed dynamics for predicting what the particle is doing. And that's the breaks.
Okay.
But what we get is a far more general framework that could accommodate far more kinds of systems. Not limited to non-relativistic systems, and we don't have to make any speculative metaphysical assumptions. We don't have to assume that we're living in infinitely many parallel universes.
Yes. Okay, great. Thanks very much.
You're very welcome.
There are a bunch of questions. I think, Chris, are you with us on the panel? You asked the first question.
Yes, I'm here.
Please give me all your questions. These are all great.
Thank you. It was a really interesting talk, and I have to apologize that my camera on this laptop is not working. But I was interested about when you were going from kind of the classical example of the permutation matrix the discrete one, and then you somehow kind of interpolated this.
Let me
wondered
go
if
back
you
to
could
that
just
slide if it's okay. Sorry.
go.
Everyone close your eyes. I know it's sort of annoying to see slides go in reverse. Let me get back to that slide. Hold on. Sorry.
Yeah, I was just struggling to follow this. I wondered if you could just go through that maybe a bit more slowly
Yeah.
so that I can see where that connection is.
Yep. Okay, so we'll start with a discrete dynamical system. So let's assume it's got n possible states, big N, capital N possible configurations. And at each time step delta t, it hops from one configuration to the next according to a fixed constant permutation matrix sigma. So gamma of t, this matrix of transition probabilities, the transition probabilities are all zeros and ones. So it's just deterministic. A matrix of zeros and ones, a permutation matrix, is a stochastic matrix, sort of trivially. So each step, we just permute the system over and over again.
Yep.
And after n steps, we just multiply n times by this matrix. Well, a permutation matrix is unitary. And because it's unitary, it can be diagonalized. So imagine you take this unitary matrix, it's just got, it's permutation matrix, it's got zeros and ones. You can diagonalize it. You can write it as a unitary times a diagonal matrix times a unitary dagger. The diagonal entries are all going to be phase factors because it's unitary. All of its eigenvalues are pure phases. And then what I can do is I can multiply all those phases, the e to the I phase. I can multiply each of the phase angles by t over delta t. Here, delta t is the discrete time step that I was assuming in my discrete process, and t is now treated like a continuous parameter.
Oh, and you can make the connection because all of the entries are 0 or 1, so I can, like if I take the modulus and square them, they'll still be 0 and 1, and this is why we can take the gamma as the unitary.
That's so. Let me get there just 1 second. So
okay, sorry.
Basically, we can multiply all the phases by t over delta t. That corresponds to taking the root, and because it's unitary, I can pull that root out, and basically so this is simply the t over delta tth root of sigma, and it's well defined and still unitary. That's the upshot of this. It is a unitary matrix, so I can take its entries and square them. And that will give me the entries of the unistochastic matrix with non-negative entries with the column sum to 1. You can actually show that it's actually not just, so unistochastic implies doubly stochastic. Gamma is actually going to be a doubly stochastic matrix. Now let's examine what this thing does. Whenever we hit a discrete number of time steps, so every time t is an integer multiple of delta t, then sigma to the t over delta t power is going to be sigma to the nth power, which is going to be a matrix of zeros and ones. And then you're right. Now, if I square those entries, I just get zeros and ones, and gamma will simply reduce to sigma. It'll just basically be the same thing as sigma. Okay.
Thank you. That makes sense now.
Yeah. It'll just, but the point is, between discrete time steps, it will have non-trivial probabilities in it. So we get a beautiful, smooth interpolation, a probabilistic stochastic interpolation between the discrete time steps. So this actually gives a very beautiful way to turn any discrete dynamical system into a smooth system at the cost of introducing probabilities. It's essentially an analytic continuation of any discrete deterministic dynamical process into a smooth stochastic process. And remarkably, one in which there's going to be a Hamiltonian, a Schrodinger equation, and all the usual stuff in quantum theory. It's kind of amazing.
That's really pretty. Thank you.
Yeah.
Okay, thanks. So I'm going to embargo more questions because we're well over time, but I'm going to try to go through the ones that have come in.
I'm happy to answer as many questions as you have. I can stay as long as you want.
Okay, great. So our PhD student JJ is asking, what is the relation between realism and your results? Are the probabilities you get in your new picture epistemic?
That's an excellent question. So you have to fine-grain the distinction between ontology and epistemology a little bit here. There's a debate over whether the wave function is ontic or epistemic, right? And you have the psi-ontologists versus the psi-epistemicists. That's a false dichotomy. There are simply more categories of things than things that are ontological or epistemic. For example, the action functional in Lagrangian mechanics, or even the Lagrangian, or Hamilton's principal function, right? The Hamilton's principal function. Are these epistemic? Are they ontological? They're kind of neither. They're mathematical. They're just mathematical appurtenances of a particular theory. What about an equation of motion itself, right? Newton's second law, is that epistemic or is it ontological? It's neither. It's a different category of a thing. Usually we use a word nomological for that, meaning law-like. It's a part of a theory that's a law. And arguably, a law is objective. Newton's second law is not something that we can just choose to ignore. You know, if you want to jump off of a bridge, like Newton's laws are going to do what they're going to do, whether you like it or not. There is an objective aspect to laws, but laws are not the same thing as physical objects. You can't hold Newton's laws in your hand. The stochastic probabilities that define gamma here, those are nomological. They're of the same status, metaphysically speaking, as any other laws. It's just that instead of the laws now being second-order differential equations, the laws take the form of these objective transition probabilities. However, the standalone probabilities, for example, the standalone probabilities of the initial time, those are epistemic in general, right? You take those epistemic probabilities and you evolve them forward with gamma, just like you would take epistemic probabilities in classical Hamiltonian statistical mechanics and evolve them forward with the Hamilton's equations. And in the case of Hamiltonian mechanics, classical Hamiltonian mechanics, you'll get the Liouville equation describing the time evolution of the probability distribution. Here you get the von Neumann equation. So ultimately, the probabilities here are going to be some mixture of epistemic and nomological probabilities. Some that are about ignorance, some that are about laws, but none of them are ontological. The wave function is definitely not ontological. It's just a convenient way to take a square root of probabilities, of these probabilities. So the wave function is of a similar status in this picture to, say, Hamilton's principal function, a mathematical appurtenance that's useful for calculating predictions, and that's it. Hope that answers your question. Does that get to your question?
Well, JJ, you can write if it didn't get.
But let me just say, in terms of realism, yes, this is a very realist picture. It's saying that systems have configurations. It's just that the laws for how those configurations, how we describe the changes of those configurations with time, are more general than deterministic laws. They're going to be stochastic laws of a very general kind. And you have to generalize them enough to get quantum theory. And some of the prerequisites for that generalization depend on concepts like unistochasticity and divisibility that really weren't available back when quantum mechanics was being developed. If you read the old papers in quantum mechanics, you can see that they make all kinds of assumptions that today we would identify as Markovian assumptions and so forth. But they didn't know they were making them because it was so intuitive to make them. They didn't have the conceptual space, maybe, the definitions and the terminology and the mathematical constructs to be able to do what we're doing here.
Okay, cool. And then there are two more quick questions. Are there any equations that govern the dynamics of gamma, and how does the Heisenberg uncertainty relation show in this new formalism?
Great. I'm glad you asked both those questions. So are there any equations that govern gamma? In a sense, yes. Because of this theorem, you can always assume, basically, that gamma is unistochastic. If need be, you might have to slightly enlarge your system by adding like a degree of freedom or something like that. And then once gamma is given by it's unistochastic, it's derivable from a unitary matrix, then the usual rules of unitary matrices will apply to gamma. More broadly, if you don't make that change, if you don't want to take advantage of that unistochasticity, well, then gamma is basically only subject to its entries are non-negative, its columns sum to 1, and usually you want to impose continuity requirements, like as t goes to 0, gamma trivializes to the identity matrix. But basically, that's it. There are no further constraints on gamma that come directly out of this formalism. That said, depending on what kind of quantum system you want to model, you may want to impose certain things like interactions between particles should only occur locally. Maybe you want to impose Lorentz invariance, and these will give further conditions on gamma. They're very difficult to impose directly on gamma. It's easier to impose them on U, the underlying unitary. And that's just what we always do. We impose all these conditions on U or on the quantum Hamiltonian, and these will then indirectly lead to constraints and conditions on gamma. There are also symmetries, other symmetries more generally we can impose on the dynamics, and those symmetries have implications for gamma as well. So there isn't like an equation for gamma any more than there's an equation for Newton's second law. I mean, Newton's second law is an equation. So for you to ask, like, what's the equation that Newton's second law itself satisfies? I mean, I guess maybe Newton's second law comes from, you could derive it from a Lagrangian, I guess. I mean, I don't know exactly what's meant there. Now, as the uncertainty principle, that's a great question. Again, I didn't have a chance to talk about it in this talk, but we can give a very simple picture of how the uncertainty principle works. So let's suppose that we'll take a very simple example, a particle, and we're taking its configurations to be where the particle physically is. And suppose I know where the particle is with high certainty. I've done a measurement, I've located the particle, it's located at some particular location. Now, if you ask what's the velocity of the particle, I guess, or its momentum, but velocity, momentum, whatever, it's just the theory doesn't supply you with an answer. We don't have deterministic equations of motion, so I'm not going to get a prediction for like what the velocity of the particle is. I don't know where it's going to be a moment from now. So my theory doesn't supply me with a statement about what its trajectory looks like or about what its velocity is. And in particular, I'm not imposing velocity as an initial condition because I don't have the sort of dynamics for which specifying a velocity is the right way to even do that. So I basically don't know anything about the particle's velocity or momentum at this point. I have maximal knowledge of where it is, but I know nothing about its velocity. Now suppose that I bring in some kind of measuring device, and the measuring device decides to do one of these measurements of the momentum emergible, right? So it has the right stochastic dynamics, the measuring device, there's an environment, all of that, and it tries to measure this feature called the momentum. Momentum is not a beable, it's not a random variable, it's this sort of emergent property. When it comes in and does its measurement, right, you just do that stochastic process I wrote later in the talk. Let me go to it. Sorry, close your eyes, I'm going really fast. Okay, we do this measuring process, and we get this particular formula here. This comes out. Now imagine the thing we're measuring is momentum. And then we condition that result to make future predictions, right? Once you condition the measuring result, the measuring device gets some answer for the thing it tried to measure momentum. And it goes, look, I just measured momentum. I think I measured momentum. Well, the new density matrix for the system is now going to be really messed up. It's going to be some messed up density matrix after this conditioning process. And in particular, this is going to be a density matrix that now assigns a non-trivial probability profile for where the particle is. So you've achieved this result, momentum. You can check that if you remeasure momentum immediately, this new density matrix is guaranteed to give you the same answer you got before. But now you don't know where the particle is. And this is exactly how the uncertainty principle works. So this is how it's realized very explicitly in this model. Without saying the particle does not have a secret position, it does. It's got some position somewhere, but this measurement process has hidden where its position is. So that's roughly speaking how the uncertainty principle works. And you can generalize this to measurements of two different emergibles. It doesn't have to, it doesn't have to be that one of them is a beable and the other emergible. You can also do this for more general emergibles. I hope that answered that question.
Thank you, Jacob.
Hugo, you have your hand raised?
Yeah.
Yes, you said that you're happy to stay as long, so I'm going to abuse this.
Go ahead.
So I was wondering, is there a difference between, in your formalism, is there a difference between entanglement and measurement beyond the fact that you said your measurement device is coupled to the environment?
Is there a difference between entanglement and measurement? Well, in a sense, yes. Entanglement from this point of view is just a loss of factorization of the stochastic matrix if two systems interact. So again, going back to that slide, sorry, close your eyes, let you know when I'm there. Yeah, so before interaction, you have two totally independent systems. They have their own separate independent stochastic dynamics given by gamma A and gamma B. If at some point they interact, then that factorization will be lost and it will just not come back because, again, these gammas are encoding all the statistical information cumulatively from 0 to all later times. Entanglement from the stochastic point of view is literally just the breakdown in the factorization of the dynamics between the two systems because you're encoding all this information, at least until there's a new division event produced by entanglement with the environment, which again is really just the environment reading off the configuration of the system and developing a classical correlation with the configuration of the system.
But so when you say the environment is reading off, because if your environment was just one other quantum particle, it can also do some sort of reading off process, but then we would assume that that's entanglement here.
Sure.
So there is a difference that you're saying between your measurement device that when it reads off, it sort of breaks things in an irreversible way, but a quantum particle would not. But
no, so you could do this. So by environment here, I said here, for example, by the environment, but you could do this with a single particle. So for example, suppose we do a very simple version of the two-slit experiment. This is an example you can do yourself on paper. It's an easy example to do. You can do it with a Mach-Zehnder interferometer, but I like just conceptually thinking of it in terms of a double-slit experiment for simplicity. Suppose I take a very coarse-grained version of a double-slit experiment, where you can do it for a more complicated version, but just for purposes of explanation. Suppose I do the double-slit experiment and I just coarse-grain the system into upper half, lower half. So I turn it basically into a qubit, just basically two possibilities. Is the particle in the upper half? Is it in the lower half? Did it go through the upper hole or the lower hole? Did it land in the upper part of the detection screen or the lower part of the detection screen? If you model the system using a generalized stochastic process, you will find that it predicts an interference pattern. If you include a second qubit that you put near the detection holes, and you give this second qubit deterministic evolution of the form that it changes its configuration based on which hole the first particle goes through, that's actually deterministic law. And actually what's nice about it is that because we're using the same formalism now for everything, we have configuration spaces, we can combine deterministic and stochastic evolution together. So it makes combining classical and quantum dynamics particularly simple, but let's actually just do it. We have the second two-state particle, this two-state qubit, whatever. It deterministically evolves into one configuration or the other, depending which hole the particle goes through. You can just use this stochastic stuff that I presented here and just directly show the interference pattern goes away. Mm-hmm. It's just a simple calculation you can do. So we would say on the one hand that there is entanglement going on here at the level of the Hilbert-space picture, but at the level of the underlying stochastic process is just classical correlation. And we get a measurement. Little qubit is doing a measurement. It's like a simple model for how a measurement works. And the interference pattern just goes away. So this requires really reframing how we think about all of these things. There is a completely boring, deflationary way to think about the measurement process, entanglement, the loss of interference, as just a bunch of particles bouncing around stochastically, reading off of each other classically. It does require a shift in frame because we're so used to thinking in terms of waves and wave functions, but there aren't any in this picture. They're not necessary.
This makes sense. So given that, we know that entanglement is completely reversible. In your picture, would that mean that measurement is also completely reversible, and these division events are completely reversible, obviously given enough control on your system?
Absolutely. What you can do is you can model like further evolution, right? Suppose we set up this little qubit so that if it takes 1 second for the first particle to make it to the detection screen from the slits, right? Suppose that takes 1 second. And suppose we modify the dynamics of our measuring particle, our second qubit. We modify it so that it forgets its result, right? We modify it so that it always returns back to its initial state before the first particles reach the detection screen. This is basically like a quantum erasure experiment, and you can show that the interference pattern comes back, but it just comes directly out of the stochastic behavior. So absolutely reversible. But of course, this is the case we expect to be true, in textbook quantum theory, right? If we assume that measurements are secretly just some very, very complicated unitary process, well, of course, we have all the usual problems that if it's really a unitary process, textbook quantum theory doesn't give us any way to make it into a measurement. Here we can. Something does happen. But the point is, if it's unitary and you have enough control, you can, in principle, reverse it. But when you reverse it, you're really reversing things back to where they were. You're really, causing systems to undo what you did to them. And you're erasing from the universe any trace of what the experimental result was. Like if there's any trace anywhere in the universe of what the outcome was, you can't do this. But you can actually show that this comes directly out of the stochastic dynamics as well. You don't need quantum mechanics for that.
Mm-hmm.
And of course, the same thing is true classically. I mean, an erasure experiment is, if I forget about quantum mechanics, just have a classical Hamiltonian system evolving, I can reverse that too. It's reversible evolution. I can reverse it and make everything go back the way it was. And if I do that, then there's no trace in the universe of what the result was. The metaphysical picture here is exactly the same as in Hamiltonian mechanics, which is really just classical mechanics, just with evolution laws that are suitably generally stochastic. So this is why I say it's actually an incredibly simple picture. But again, a picture that would have been difficult to imagine without understanding how far you could generalize stochastic dynamics.
Mm-hmm. Great, thank you. Thank you very much.
Okay, thank you so much, Jacob. I think we just have a super quick closing question, maybe, which is someone in the audience wonders if you have a catchy or swanky name for your new theory.
Well, it's called the Stochastic-Quantum correspondence. I don't know how catchy that is, but it is literal. We're saying that every quantum system is secretly just a generalized stochastic system in disguise, and we have this detailed correspondence. If you want like a name, like, is this like an interpretation of quantum theory? What would we call it? Unfortunately, stochastic interpretation is taken. Other people have taken this. The name I kind of like is, so again, going way back, and I apologize, close your eyes. I'm going to go to the very beginning, the first slide. So close your eyes, wait. The pithy one-liner. Let's go back to the pithy one-liner. Hold on, sorry. I'll tell you when I'm there. Okay. The universe is in some configuration evolving along a trajectory governed or described by a stochastic process, but in particular by an indivisible stochastic process, because generically unistochastic evolution will be indivisible. So for want of a better term, I've been calling it the indivisible interpretation.
And I think that is catchy.
Perhaps, yes.
Okay, Jacob, have a very nice day over in New Cambridge, and thank you again for joining us today.
Thank you. I really appreciate the invitation, and I appreciate everybody taking their precious time and spending it here in this talk. If you've got follow-up questions, please feel free to email me. I'm always happy to talk. Yeah. And there are a lot of open questions here, so if you want to work on any of them, let me know.